So we introduced the concept of cyclic voltammetry or CV, and we showed the example, the simplest example, which is a resistor. Now let's look at a different example, which is CV, cyclic voltammetry, for a capacitor. For a capacitor, same as before, you have potential across a capacitor versus time, and you linearly drive it up, linearly drive it down, linearly drive it up, drive it down in cycles. Okay, and let's say the voltage ramp rate is dV over dt. How fast does voltage change with time? You give it linear. That number is V, and it's in the unit of volt per second. Okay, of course, when you ramp up, this V or the ramp rate would be positive, and then when you ramp down the voltage, this V value will be negative. Okay, so for a typical double layer capacitor, let's just for simplicity show it here. You have a capacitor, that's what you learned in physics. You have ampere meter to measure the current, and you have voltage. You have a voltmeter to measure the voltage, and similar as before, you can use a potential stat or galvanostat to drive current, charge, discharge the capacitor, ramp the voltage up, ramp the voltage down. Okay. During the charging or discharging, during the charging and discharging, remember the dq, the small incremental change in charge, Q for charge, dq would be the current, instantaneous current times dt, the incremental time. So the incremental charge is just current times the incremental time, a very small period of time. And then for capacitor, remember by the definition, the capacitor capacity is related to Q by the voltage. So this incremental charge for capacitor will just be the capacitance times the incremental change in voltage across the capacitor. That's what you also learned in physics. dq equals to C, capacitance for this double layer capacitor, dl for double layer capacitor, times dV, the incremental change in voltage. Okay, so you have a small incremental increase in voltage, you have a small increase in charge, and that charge is related to current by small period, because you need some time to charge the capacitor to get more charge onto the capacitor. Okay, and then based on this, current, which is I, would just be dq over dt. Focus on the first two parts of this equation. Current would just be dq divided by dt. Okay, that's what we learned in physics. Current is just the incremental change in charge divided by the incremental change in time. And the current, based on the following part, would be just C, capacitance, times dV over dt. Looking at these two, looking at the later part, I would just be C times dV over dt. Okay, dV over dt, that's essentially the ramp rate for the V for voltage, ramp rate for the voltage. How fast does voltage change with respect to time? And then remember, we give the definition dV over dt defined as small v, velocity or ramp rate of voltage. Then we can write the current would just be dV over dt, which is V times CdL, the capacitance for this double layer capacitor. Okay, so we got a simple relationship from what we learned before in physics. Current related to ramp rate of voltage times capacitance. And then if we have linear ramp rate, let's say ramp up, we would have this ramp rate of voltage would be V would be constant, and CDL for a given capacitor, the capacitance is also fixed. What it means is we would have constant current. V constant for linear ramp. CDL for given capacitor is also constant, so we would have constant absolute value of current during the charging, and then for discharging it's constant slope, constant ramp rate. We would also have constant current, okay, except the polarity would change. So if we plot E versus T, potential versus time, this is our cyclic voltammetry. Then we measure current versus time. We would have constant current positive for charging, and then constant current negative for discharging the capacitor. And then similarly, for the next cycle, constant current for charging, negative constant current for discharging. Okay, and the current change sign, or what we call polarity, from positive to negative, from positive slope to negative slope for the ramp rate upon reaching this limiting voltage. So there will be a sudden change in polarity of the current as we go from ramp up to ramp down, from ramp down to ramp up. Okay, so if we plot similarly as before, current versus potential to get the CV curve, cyclic voltammogram curve, current versus potential graph, we would have essentially, under ideal case, a square. A square. You cycle the potential, and then when you ramp up the potential, current positive, and then reach limit, go down, you ramp down the voltage, the current is also constant in value but negative. And you repeat this, it goes in certain direction. Okay? And this is the CV behavior for a capacitor, double layer capacitor. When we linearly ramp up the potential, ramp down the potential in cycles, we would have constant current for charging, constant current for discharging. And then charging, for example, could be one polarity, in this case, for example, positive. The discharging could be negative. Okay? And the CV curve looks like a perfect rectangle.